Hi everyone, welcome to the day 24 of the training in the FPGA development. I am so glad that I've been teaching you all these most essential understandings and learnings of the designs in the FPGA development. These are internal blocks of FPGA that are to be developed in the architectural way. And coming to the today's agenda, we will be opening the Xilinx vivado EDA tool and we will be understanding what type of design we need to implement in terms of memory design. And as we have already done the implementation of memory design in EDA playground with 64 by 64 RAM design, that mem design, that today we are going to implement that type of memory design in the vivado tool. So let's go to the today's agenda. Implementation of memory modeling using Xilinx vivado. Understanding of the design, test bench and timing simulation. Got it? So we are now understanding the design. We will also open the implemented design. I will try to implement the design after successful simulation and synthesis, and then at the end I will show you the entire block design, how you have designed the FPGA architecture in terms of memory. Now our main focus is to turn your FPGA chip into a RAM, into a 64 by 64 smaller memory. Just basic application. It's kind of project implementation. Let us go to the memory. I would like to jog your memory with implementation. Let us consider a memory of 8 data address of 3-bit and data out as 8-bit. Let us now consider the read-only memory block like ROM or EEPROM. A basic example of ROM and EEPROM. In that EEPROM, electronically erasable, programmable, read-only memory. Okay, so this can be reset electronically by the electronic pulse, and read-only memory is nothing but you can only read from the memory. So whatever the memory you have, some information, piece of information here, some information, for example, some has sine wave and some has sawtooth waveform. Some information you have, some have square waveforms of data. So all these data that are available in the read-only memory can be taken into data out. So in this we can use the case statements for the memory design like shown. How are we using case statements now? Module ROM, for each bit of data, each bit of address location, we have total 8 address locations for the 8 data. If you want to mention this memory register, we can mention as it's only read only, and we have 7 memory and each has some data, that each has 1 byte of data, let us assume, and you have 7 location. So 7 by 7 is your matrix of memory. Okay, so input address locations, you have 3 inputs. As you can see 8 address locations, your data should be 3 bit. So let us see, you have 8 address locations that can be written in terms of 2 power 3. So this is the value of number of bits, and 8 is the number of locations. Okay, and you can see output register, the input are nothing but read enable signal. So you will have a read signal as in the earlier design, read signal, read underscore enable, or data underscore read, anything. anything can be command. Okay, that can be command. Output register data out. All outputs are registers, that is 8-bit data out, because you have 8 bits of data here. That 8 bits should be sent through data out. So always at the rate of inputs, when address value is changing, read enable signal is changing, chip select is also enabled, then the actual procedural block starts with the case condition, with case at 0 location. So you can write this as 1 bit 0, or you can also write it as 1 bit binary 1. Okay, or you can, or you what you can write is, you can write 3-bit binary 0 0 0, or you can write 3-bit binary 0 0 1. 2 can be represented as 3-bit binary, what is the value, for example 0 1 0. So let me write that for you. Okay, so now all these address locations can be seen at these different address locations for the 8-bit address. Because why 8 locations? Your memory, you are looking at 8-bit out data for 8 different locations. As a random example, if you are choosing 100, this is the 4th location, it will go through the address, and this is selected, and 0 1 2 3 4, 4th location is enabled, and whatever the data is there here in terms of 8-bit data, that is sent through the data bus. That's our agenda. So in this we have 69, so that can be represented in 8 bits like 0 1 1 0, and 9 can be represented with 1 0 0 1. Got it? And that data is in address number 4, and that that data is sent through data out. That is what the meaning is data out. AND case and AND module. Hence it is done. Thank you. So now let us go to the memory location. Now we are taking the consideration of memory block with memory 64 by 64. As you all know, in out bidirectional is used now. In the procedural block, we are not using bidirectional anywhere in the read process. So in the read process, we are taking the data from mem address, whatever the address is there in mem register, that is taken here into the consideration of data underscore register. So coming to the points, this is first part, first step, and this entire thing can be, sorry, so this in out and outputs are declared here. This is second step, and registers are declared in third step. What are the registers we have? Data reg, this can be temporary register. I'm just adding a comment lines, don't worry. This is a temporary register, and whatever the input is, it is address input, and memory write and memory read is the inputs again. Those are the signals. For example, in the design, you will see read signal, right? You can also see write signal. We should enable this because when did we want to write, when do we want to write the data into the memory, and then when do we need data to be read from the memory? So don't get confused. That is why we are giving mem read and mem write signals, command signals. Those are command signals. Command signals can be just write and read as well, not to be heavy enough like mem underscore write, because I'm writing mem underscore write in a basic declaration because in the memory, if we are using this in the next block or next any other diagram in the real-time application, we shouldn't be getting confused. So hence it should be very specific when you are mentioning the variables for the names. So data bus, memory write, memory read, and address. Okay, so and after you mention this, after three parts, fourth one is initialization. That is initialization. And sometimes we need to read the data from underscore c users vivek mem underscore block and input.txt mem file. So whatever the data is there, that can be read into the memory. Got it, guys? But unfortunately in this version of 2015.2 version of Xilinx vivado, we are unable to add input.txt file. But in the latest versions, you can add an input file as you have done in the EDA playground, and you can use that input.txt file for the data process. And here we are displaying the data, like data is written, write process is done initially all the data write process is done, because whatever the data in the input text file, you have seen input text file data as 0 0 0 and have these 8 bits of 0. This is the 8 bits of zeros, and you also have seen 8 bits of 7s in the input text file we have seen in the previous lecture. Please go through it. And now you can see data process is done, write process is done as you are writing into the memory, read mem h. Okay, hexadecimal data, hence you can see the values 7, and if it is more than 15 you can also see f in the okay, and one more f, like you can see 16 values. Okay, then always at the rate procedural block. This is the fifth step after initialization. This is fourth step. In this process we are mentioning, if you want to write the data, write signal should be 1 and read signal should be 0, or else read signal should be 1, else at the initial default state data reg is here, one data reg, let us name it as data reg, temporary register to hold the data like a cache, that should be at high impedance like hg. 64 tick hg is nothing but 64 hexadecimal z. Z is high impedance, it is a open thing. Hence start from the if else condition. If memory write is 1, 1 bit 1 is 1, memory write is enabled, this command signal is enabled. Now this command signal is enabled, so data is written into the registers of memory, right, from the data in, where, from the data bus. From the data bus, let me make it more clear. So when write enable signal is given, this shows that from the data bus you can write the data into the memory, but for which location we have to write, that location is given here. That is the meaning of mem address data underscore bus. Okay, so after that, else if it is write condition. Now let us talk about read condition. So else begin, it is read condition. So in the read condition, now read is enabled, hence read is nothing but whatever the data you have, that piece of data should be sent through data out. I mean via data register and data register to data out. Okay, that is it. That is the meaning of from the memory address you will be writing to data reg, and that data read address is represented here. But you can also see at the end whatever the data is there, that can be stored into the data bus in a in out bidirectional. We don't have data out here, but only through the data bus we are collecting the data. Hence it is in out. With one single bus there is an input and there is an output here from the memory. Okay, so this is the test bench. As you have understood this test bench in the previous lecture, I'm not repeating this much, but you can see the structure. How did I mention and instantiate this entire process? Go through the test bench code, and if you have any further doubts, just please let me know. And now let us go to the memory design. This is how memory implementation is happening in the 64 by 64 memories. So each selection is one register here. You can see there are 64 registers. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 and so on. So you can see 64. Here you can see the registers. I will be showing this entire implementation in the Xilinx vivado tool. Let us open the Xilinx vivado. I'll come to this part after the Xilinx vivado explanation. I can zoom in the vivado tool itself. Now this is how our memory design looks like. The design file .v is design file, _tb is .tb test bench file. For adding test bench file, I hope you have remembered, add sources, click on add sources. For example, in the new project, you will be seeing, click on next. How you have to mention some name. I am mentioning RAM 64 under 64. Click on next and click on the RTL project. You should not mention any specific sources at any time. At this time, at the point of time, because you have to go through this all RTL analysis, synthesis, implementation and design planning and analysis. So this entire things you have to do. Then next, you can add or you can not add any other source file. Just keep it as it is. Click on next and click on next. You can finish it, and then I'm not doing it. I have already done this part. Then you will see an appearance file of a .verilog file here in the design sources. In the sources, follow along my mouse cursor so that in this .verilog file you can see timescale 1 nanosecond and 10 picosecond or 1 picosecond. This is mentioned. In the second thing, I have declared the module name in out, input, output. In out is nothing but from the data bus itself we are writing or we are getting the output. So input and output is both synchronized, and after that we have written input memory write signal and memory read signal, when to write and when to read the memory. So then input address register, address location should be known. As we are talking about 64-bit, so we have to have 6-bit address. 2 power 6 is 64 inputs, right? So 64 locations. Reg 63:0 is data reg. We have mentioned as a temporary register, and memory representation you can see. This is how many bits per register in the horizontal column, and this is about depth of the memory declaration. This entire Verilog HTML code is not new, but was explained in the previous lecture. Initial begin initialization, read from the .txt file. Here it can't read because if I have written in this way, this input.txt file should be added in the source files, in the resource files, but unfortunately in this version I couldn't find anything to add this input.txt file. Even after adding all these type of files, it cannot take the .txt file by that version. But later in the advanced versions, in the latest version, some of you might have been using 2019 2020 versions as well, 2022 versions as well, if you have some basic license. And you can add some input.txt file, and that txt file was discussed in the earlier version. Please let me know if you want any input.txt file. Basic thing, you can write 8 bits of or 64 bits of 000 and 77666 all 8 times you can repeat the same number in a single row. That is your input.txt file. And ns data is data write process is done, because whatever the data is there, that will go to the mem file. And impedance, this all loops are explained till now. Now let us go to the test bench file. After you declare the module and registers and wires, you can see this instantiation. This instantiation is same as it is. You have to write the input and outputs like you have written in here. Come to the initial begin. All the memory write and memory read signals are 0. Address should be at 0. After some certain point of nanoseconds, you can write this thing, memory read and memory write. Actually, in the previous lecture, in the previous day of the lecture, I have mentioned this in the EDA playground. Today, I have been using this in the Xilinx vivado. And see, I have commented this. I am not using this waveform generation. Why? Because this is an EDA tool. It has an inbuilt simulation thing. Now let me run this simulation part. I can run it. Run behavioral simulation. In the down below, you can see the log files and TCL console, and you can also see messages, and you can see the log file in the messages, and whatever the waveform that is generated, you can see the data here and some random data. And if you minimize it, you can see it in the nanoseconds. Control plus scroll down, and you can take it to this point, and you can see the address locations representing these different address locations. Why? Because we have given these address locations in this way. Let me take this out, and you can see this address location. First address location is hexadecimal 7, and that is hexadecimal 7. Okay, I need to take this out as well. If I have taken this out, how can I show this as well? So you can see both of them. Now in the address, in the test bench, this is a test bench file. You can see mem_tb is a test bench file that we have written. In this hexadecimal 7 at this address location, after some 20 nanoseconds, after 20 nanoseconds, see, after 20 nanoseconds, my address location changed to 7. I have written as 7, but I have to get the data from data bus. But in the design file, what is the data bus that I am getting here? I am not getting any data bus file, any data bus. I don't have any data bus, because I'm not getting any memory here. That memory should be coming from this input.txt file. No, I'm not getting it. So hence data reg is empty. Due to data reg is empty, database is empty. That is one kind of application. Hence for every address location, data bus is empty. You can see this data bus is empty. Sorry, this data bus is empty. And if you can see at the second location, what is 110 called as? 110 called as 6. I mean, yeah, it is 6. So that is 6. and 111 it is 3. And if you notice another thing, address location is 6 bit, 000 110, 6 bit, 000 111, 6 bit. Why 6 bit? Because our data bus, our data is 64 bit. See, for every 60 everything we have no value written. But if you have some .dat file or some data file, you can always mention that into this, and you can write that text file here, and memory design, wherever the memory design location is present, in that memory location. See, in my condition, users Vivek memory block, in my local machine memory block design, that memory block project, my project name is memory block project. So in that memory block project file, I can see that text file is available. So that is it. That is how you can run the simulations. I hope you are getting an understanding of this entire thing. Now after simulation, you can run the synthesis, or you can elaborate open the elaborated design. But after implementation, usually you can open the design, but before implementation, let us run the synthesis. So yeah, save. I have moved a little bit, right? So I need to open the synthesis. After synthesis is done, it will open. Okay, synthesis is open. Let us open the synthesized design. Let us see what it is looking like. Yeah, this is a little bit fuzzy with the. So now you can see the block representation of the entire design, synthesized design. You can also see the device, and that device, if you can zoom it into the larger screen, and if you go inside it, all these blocks, all these configurable logic blocks, these are CLBs. You can see this is CLB, configurable logic blocks. Whatever the functionality you want to derive, you can connect them in between, and that connection will happen now in the memory design, and that connections will derive you an output. So this is how it looks like. And all these cells, see, this is some multiplexer. So this is multiplexer. This is a lookup table. Lookup table is nothing but a memory, some kind of memory. See, in the type, and that site, that location and tile, this is the tile, and that is a nomenclature given inside the EDA tool, inside an FPGA, you can see. And what else you want? This is a demux, and also this is an XOR gate, carry 4 XOR D XOR 4. You can see these are mentioned in these names, and those outputs, this entire thing is one register. Carry 4 is one register. LUT represents a lookup table, and see, every block or every cell has D flip flop. And what is this called? Init and flip flop initialization and clock enable, clock output queue, all these things. That is what we are designing in the everyday sessions, the lookup tables. So some other parts, you can see the pads in the output and input pads, and this is a monitor device. You can see the name, and some other configurable logic block, CLBs, and you can see this as one of the logic. See, logic. um, those logics can be written by us. Those will be defined by our designs, and whatever the designs you want to use. So let us go to the IO buffers. See, IOB is nothing but IO buffer. IO buffer. What is x1 y1? It is nothing but a location. For this location, see, x1 y2, x1 y3, x0 y2, and what is another thing, x1 y1, x0 y1. These are locations of blocks, different blocks. And see the IO buffers here. And we are not using unbonded. These are not connected. iPad. So see all these configured blocks, and they are separated between these logics. Okay, DSP blocks, and this is RAM. See, you have RAM blocks, BRAM. Here you can see BRAM, memory block. These configurable blocks are separated between block RAMs. Another RAM, it is having some kind of data, and also this is having DSP block, so digital signal processing. You need to define everything, how these will be uh, operated with each connections, and see if you can zoom between two configurable logic blocks. So this is one CLB and this is another CLB. You can see buffers. Buffers are nothing but connections of peripherals, two blocks that can be communicated through the buffers. See, that is the architecture, basic architecture. Now, by using all these cells, how will you connect them? How will you connect them internally, and how will you use them? Each logic cell, each XOR gate, each demux, each multiplexer. See, each 2 by 1 multiplexer. Yes, if you represent two 2 by 1 multiplexers, what are you getting? You are getting 4 by 1 multiplexer. And you are using three 2 by 1 multiplexer. What are you getting? Some kind of multiplexer out of your own design. So in this way, all these cells are combined called as configurable logic blocks. So let us connect this into this. And package is nothing but this is how your chip look likes. So square chip and all these ballings, and also you can see ground and power. VCC INT is nothing but power, and see this VCC BRAM is nothing but this is powering the block RAM, and some other GND, this is ground for everything, commonly called as, and this entire tile block, and some other ADC. See, ADC, oh, we lost it. Yeah, ADC controls, and VCC and GND ADC controls. See, one initialization init and all these buffers. And now after synthesis, in the synthesis you can do lot many things. You can report the time, and if you have any DRCs, design rule checker, you can report the DRC. Or now let us go to the implementation, the next step of the design. Okay, so implementation might take some time in the design. So this is a block level bifurcation of the design. See, XADC, and these are connections, and what is this called, this block called IO bank, input output blanks, and these are the ballings somewhere, and these are the pins. You can mention pin locations. See, this is F. In the left side you can see F and 4, F4 location, and F3 location, F2 location. So these pin locations will be helpful for our IO planning. So this can be connected to this connected. No, I don't want to ruin the design while it is getting implemented. But see, in the implementation you can see here what process is happening. From the placement it is going to the routing. Routing is nothing but connections, and after connections of the route, nets are connected, that is nothing but routing. After routing it will go through the optimization phase mostly. Optimization is nothing but the best routed design between two configurable logic blocks. For example, if you can see this device, and if you can, and if one route is connected in this way, if it is shorter route, that is okay, but if it is connected in a complicated way, that should be optimized. So that is another topic of optimization in the entire design of the chip. See, everything matters, everything comes out from the experiences, so you will get a better understanding. Let us not get too much confused. Let us understand, okay, this is the entire chip. So inside chip we have blocks, and so for that blocks you have DSP buffers, DSB blocks, block RAM blocks, BRAM blocks, and implementation. Open implemented design. Okay, yes. So those design windows will be opening again because those are synthesized design. Those are not implemented designs. Now after implementation, the actual Verilog code, the entire design what you have written, that will be sitting on the device. See, now before you haven't seen this, but now you are seeing these are active. Okay, let me take into the bigger screen. Now these are active. Now this D flip-flop has been considered as a buffer. So see, those group of cells are active and those are connected internally. I will try to show cell connections. See, these are the cell connections. Okay, and it will be too much confusion. Okay, what can we do? Okay, let us see. See, if one thing is selected, how these are internally connected. See, this S0, see, for this only cell, this S0 is connected to some other IO pad, like some other IO buffer output. So from this address location, we got one address location. Let us say 1 or 0. For that 1 or 0, we need to go to this cell, and that cell will be, it is connected to data bus. See that selection, data bus, and that data bus is taken to this entire data bus selection for the output. That input is selected, and if it is 1, this data selection is done and data is gone into this output. But how do we get the output here? Whatever the output is there in this block, from this lookup table, see, data is coming to the lookup table at 0 and 1. Now selection S0 is done. So that S0 selection is somewhere here in the IO buffers again at the IO buffers. So selection, now let us say the output selection is 1 again. So that one output selection selects the data from this lookup table. If it is 0, from this lookup table we are getting. So it is 1. So whatever the data is available here, that is taken to this one point and it is considered to this output, and this output will be sent to this selection buffer, and in this selection buffer you can see the output is here, and this output remember, this output is connected to one of the input lookup table, one of the input lookup table. Okay, now if I connect this input lookup table, the output is connected to this output is connected to IO buffers, and the output is selected in this way that can be read out to the external peripheral. So that is the reason these IO pads are functioning. Okay, now let us take this consideration. What it is saying, IO buffer alias pin name VN0, and this is how this entire data is entire FPGA chip. You have made this cells active, and that active cells combinedly called as a memory 64 by 64. Got it, guys? Imagine I have explained only for one register of data, how it is transferring, but we have 64, right? It should be processed in this way, and in this some buffer gate controls, see all these external buffers, some buffers are again operated here. Okay, all these are controlled by gates. See, all these are controlled here. These are buffer control logics. These are the connections. Usually these connections didn't look like this, but we have a set of wires in horizontal and vertical patterns. In the IC design you will be getting to know. So that is it. You can see the design. That is the implementation of the design. Later you can generate the bit stream here, and after generating you can open the hardware manager here in this way, and open the target. If you have board in your hands, you can upload the target and you can see the data there, and that's it. So I think you have understood everything of it. And for a short review, to understand what is the data flow, or what is the flow of the development of the FPGA design, this is the reference from the Xilinx ISC vivado tool. You can see the RTL development, and from that you can see the IP package integrator that we have seen. From that you can see the configure IP systems if we have, or else simulation, functional simulation we have done, and we have gone to the synthesis. Logical and physical constraints, if we have a constraints, we will be adding the constraints file and logical synthesis, and then go to the timing closure and design analysis. Usually that can be done in the design automation. In the FPGA designs we can also do the timing closure and generate the bit stream, upload it to the processor debug, and we can give the hardware bring up and validation, checking on the hardware. So meanwhile you can see the system design entry. This is the entire system design entry. If you have stuck at any other point, you will be redirected again back to the previous step. So export to the SDK after generating bit stream. If you want to run some C program on it, we have to export to the SDK. This is the development of software or processor OS. Like we had developed Microblaze and run C programming on it. That is the overall recap of it. So this is the FPGA. If you connect this, you can upload the bit streams. Entire data or the design will be turned into bit stream, ones and zeros, that can be turned into FPGA application. So this machine will understand only 1 and zeros. If you have any questions, please let me know. Thank you for being consistent, and see you again. Thank you.